Okay, so in the last video we went over a few things that we needed to remember, and then now in this video we're going to touch on nodal analysis. Let's get into it. All right, so the thing to remember with all of these different techniques is that they're just basically techniques on how you could analyze a circuit. What does it mean to analyze a circuit? It's just ways that you can get to understand what's happening in that circuit in terms of voltages, currents, resistors, and it might seem a little bit trivial, but as you advance forward, it does become actually very useful. So the technique that we're going to cover here is nodal analysis. I'm not going to go too much into it because, like I said, this is revising more so than teaching. So if this is your first time ever going through nodal, maybe watch this, but probably better to go through a book or something. All right, so let's just revise what a node is, in case you've forgotten. So it's a point in a network. I covered this in 2 videos ago. A point in a network or in a diagram or circuit. A point in a network or diagram or circuit at which lines or pathways, right? So like connections, intersect or branch. Right, so if you think about like a neural network of something like this. Yeah, so each one of these is a node, right? So in terms of circuits, if you had a circuit, let's say another resistor here. If you had this circuit R1 and R2, then there are no nodes in this circuit. But the moment you add a resistor here, even add another one, add a current source if you want, the R3, R4. Now you have a bunch of nodes. So the nodes exist one here, one here, one here, one here. So you've got 4 nodes. So if you look at what the definition is again, a point in a network or diagram at which lines or pathways intersect or branch. So you think about it, right? The way I like to look at a node is that if I've got electrons firing out of this battery, right? Even though that's not what electrons do, but they go through this resistor, come back, and come to here. If the only way they could go was down here, then that wouldn't be a node. But since they can branch, and now the electrons are split, one's going, some are going this way, some are going that way, and that shows that that's a node. Even if you look at the ones that manage to go this way, then when they get to here, they branch again. They can go this way, or they can go this way. Right, so it's a point where they meet, right? This would be a node, you can call this node A. This would be another node, you can call this node B. Another one C, and another one D. So nodal analysis, we're basically using these nodes to analyze the circuit. So let's briefly go over the steps, what's involved in nodal analysis. So steps. So the number one thing that you've got to do is label everything, and I'll clarify this later on. Number 2 is to do the current equations. Again, if you're revising this, then you should know these things, but I'll go into more detail. Current equations are basically I is equal to VR. It's used V divided by R, sorry, which is the Ohm's law equations. Then you've got the KCL for each node, KCL for each node. And if you really aren't familiar with any of this, go back and watch the other videos or jump onto another video, because again, like I said, I'm just revising. So number 4 is to substitute so the I's meaning the current equations here. You're substituting them into the KCLs. Again, I'm going to go into this in more detail. Number 5 would be to do all of the simultaneous equations. That's basically using each of the KCLs. And then number 6 is to calculate the currents using the nodes. And that's it. So it seems a bit complicated there, but it's not. It's fairly straightforward. So in terms of labeling everything, the thing to remember is you've got to label the nodes first. So ABC, like I've done already. You've got to choose a ground. You've got to do the currents. You'll see an example of what it means to label nodes and label grounds. It's basically when you're doing like A plus B and doing the arrows and stuff like that. Okay, when it comes to writing the I equations, then you're thinking of things like I is equal to V1 plus V2 divided by 5 ohms. Those kind of equations. Again, we'll go through that again. These are the steps, so I'll go into this in more detail now. But when I was learning this, I tried to make sure I just memorized. Okay, there's 6 basic steps. Label everything, do the current equations, KCLs for each node, substitute the i's into the KCLs, do the simultaneous equations for the KCLs, and then calculate the currents using those nodes. So I just memorized those 6 steps, and then it was a lot easier for me in my exam and everything else. Let's touch on, because this actually gets complicated. Let's go through labeling currents. So when it comes to, I feel like I need to probably, before we're going to do an example anyway. So if you don't get it, that's fine. But this part here, the labeling everything, it caused me a bit of problem. So I just want to touch on that a bit more. So obviously we said that we're going to label the nodes, we're going to label ground and label currents. Hopefully you know how to do this. But in terms of labeling currents, the template that you need to kind of think about is that you're just doing V equals IR, right? And so we're dealing with the currents, so we're basically doing I is equal to V divided by R. Now, V, in terms of the nodal, when it comes to nodal, we don't know the voltage. So for example, like finding out the voltage here, like what could that be? That could be anything. If this is 12 volts and that's 5 amps, what's this voltage here? It's gonna, you don't know basically, right? After all these voltage drops, you don't know. So what you would do is you would basically do it in terms of ground. So in reference to ground, what's that? And so you end up with this kind of template of I is equal to the voltage high. And again, I'll go into this in more detail when we do the example. Minus the voltage low. All of that divided by the resistor value. Resistor N, whatever the resistor is. Now, when it comes to choosing which voltage is high and which voltage is low, this is another important point which gets confusing. So let's just put voltage high versus low. Let's take here. Copy it. Brilliant. Okay. So in terms of the writing the current for this, right? We need to pick a current. We need to pick which one of these is going to be high to low. And if you think about voltage, in terms of voltage, the potential difference across something is from high to low, right? So if you say that the current is flowing this way, right, then what we're saying is that the voltage across this resistor, so the voltage here is going to be A minus B, right? And then the current there, so let's put current, thinking about I is equal to V divided by R, thinking about that, right? The current here is going to be therefore A minus B, all of that divided by R3. Because why? The potential difference is, or voltage is, current flows from high to low, right? So if we're saying that current is flowing from here to there, from A to B, that's the way that current's flowing. If we're saying that, then what we're saying is that point A has a higher voltage than point B. So therefore, when we're thinking about our template for labeling currents, we're always going to put V high minus V low, right? So that's the potential difference between ground divided by R. Okay, hopefully that makes sense. I mean, I'm probably not explaining it great, but you'll get it more when we do the example. So let's copy this again, and I'll do one more example. So if we say that the current is flowing this way, when we do nodal analysis, we'll always label all of the current directions first. It's arbitrary and it doesn't matter, because when you're working out your equations, you end up with minus, and then you'll know that you labeled the current the opposite way. But if you label the current going this way, then in this example here, it would be, the voltage would be B minus A, and then so the current would be B minus A divided by R3, and that will equal the current. Let's say I3. Cool. Okay. So definitely, it's one of those where I think, you know, if you haven't done this for a long time and you're revising like me, then you're probably going to learn best from an example. So let's just get started on an example, and hopefully it'll start to make a bit more sense then. Okay. All right. Let's draw a circuit, and we'll do a circuit with 2 nodes. So Let's go resistor here, put a current source here. Let's put another current source here. This is like the basic circuit that we did loads and loads of times in our first year, so probably best if you get used to this one. So here you've got two nodes, or two main nodes, and then your ground here, but let's not do that yet because that's part of step one. So let's say we've got this circuit. Let's just give everything some values. R1, we'll give it 2 ohms. Let's give this current source 3 amps. Give this current source 2 amps. Let's give for this one R2, and we'll give it 5 amps, 5 ohms. I'm drunk saying amps, 5 ohms. And we'll give this one R3, and let's go 4 ohms. Okay, so where are two? Okay, wait, let's go back and copy our steps actually. So we've got, this is our circuit. Go back to our steps, copy this, we'll have it with us. So for my exam, my examiner, he allowed us an open book, so I basically took in these steps here. I eventually ended up memorizing them, but it's all good. Okay, so first step is to label everything, right? So let's basically, what we'll do is we'll put a ground first. We'll set ground to be here, this point. We'll label our nodes. Go over node here, node here. We'll call this one node 1, this one node 2. Okay, and then let's do some current. So for R1, if we say that, you know, we've got, well, for here we've already got two current directions already. We know that this current is going this way, and that this current is going that way, so we can label those two. Then if we say that the current goes down here and goes down this way, so let's draw current that way, and then we'll say the current goes that way. And the final one that we've got to do is this one here. So how do you decide where the current's going for that way? Again, like I've said, it doesn't matter. Whichever way you do it, it will work itself out in the end. So let's just say, seems to me like the whole circuit's going this way, the current. So let's just say it's that way as well. Alright, so one thing we know is that obviously current is going to flow from positive to negative. So we can now label all of our resistors as this is the positive end, that's the negative. Put it outside so it doesn't look like a voltage source. Positive, negative. We know that this one's positive, that's negative. We know that this is positive, that's negative. Okay, and so that's it. So now we've done step one, we've labeled everything. Okay, so now the only thing that we didn't do, we didn't give our two current sources names. So let's just give them names. So we've already got R1, R2, R3. So we can call this one R4. Call this one R5. Sorry, not R5, I5. I4 and I5. And you'll see why that's important in a minute. Okay, so step two. Okay, so step two, probably the most important step of the whole thing now, is to label all of our, or to write all of our current equations. If you don't know what I mean by current equations, what I mean is that the current here is I1. We've said that this one's I4. We've got this one as being R2, so the current here is I2. This one's I5, so we've labeled that. This one's going to be I3. So what we have now is we can write the equations for each of our 5 different currents, right? So we can put I1, I2, I3, I4, and I5. Now we already know what I5 is, which is 2 amps. We know that because obviously that's that. We know what I4 is. I4 is 3 amps. Those are all sorted. Now, how do we find out I1, I2, and I3? We have to go back to this template that we said. We're going to use this template here. Copy and paste it. Save this here. Okay, so what we're saying is that the current at any point is equal to the higher voltage minus the lower voltage divided by the resistor. So let's start with I1. I1 here, what we're saying here is that the current is equal to the highest voltage, which is here, minus the lower voltage, which is here, because remember current is flowing from the higher voltage to the lower voltage. So wherever the current's beginning from, which is here, this is going to be the highest point of the voltage, and where it's flowing to here is going to be the lowest point of the voltage, right? So we're saying that current's going to flow from the highest point to the lowest point, or from here to here. Now we know the voltage here, right? How do we know the voltage here? Because look, ground, right? So we know that this point here is ground. So what we can say here is that I1, the higher voltage, and I know this sounds weird, the higher voltage is ground, but we're using this ground as an arbitrary ground. It's for reference, so yeah, the higher point can be ground basically. So we're saying that I1 is equal to ground 0 minus the lower voltage, which is the voltage up here, right? Now what can we call this voltage? Well, we've said that, so in terms of, if you used to label this bit here, how would you find out what this voltage is here? Well, if you look up and go over here, we know that this voltage here is equal to this voltage here, right? Because there's no voltage drop, nothing going on between here and here. So these two have the same voltages, and so we can just say that this is V1, right? And we can do the same thing for here, V2. So now we're saying that the voltage across this whole resistor here is ground 0 minus V1. So we put 0 minus V1, and then we can divide that by the resistor value of R1, which is 2 ohms. Right? And then another way to look at that is that you could just write minus V1 divided by 2. So the current at I1 is minus V1 divided by 2. And so once we finish writing these current equations, now all we'll have to do is just find out the voltages at N1 and N2, or node 1, node 2, or V1, V2, and then we can easily find out the current. Okay, and then obviously we've already got the resistor values. So let's do I2. So I2 is probably the most confusing bit here, but it'll be alright. Remember, we've said that current's flowing this way, right? So again, we just stick to this template. If you stick to this template here, you'll be fine. If you start thinking about it too much without really understanding electronics, you'll probably get confused. So don't think about it too much. Don't think. Just look at the equation. Alright, so we've got V high minus V low. So we're saying that current is flowing from here to here. So the higher point is V1 and the lower point over here is V2. So we can just say that the current at I2 is equal to V1 minus V2, all of that divided by the resistor value. I don't know what it is. It is 5 ohms. The V1 minus V2 all divided by 5. Now remember, this is all just basically coming from V equals IR, right? V equals IR, and I is equal to V divided by R. Right, this is where we're getting all of this from. Okay, final one, I3. So I3 now is just the opposite of I1. So we're basically saying that current is flowing from here to here. So the higher point voltage is here, and we've said that here is equal to here. So we can say that it's V2, right? And V2 take away this point here. We know this value here because it's equal to that. These are going to be the same value since there's no voltage drop across here. So V2 minus 0, or you could just say V2. All of that divided by the resistor value, which is 4 ohms. So you could just say I3 is equal to V2 minus, or V2 divided by 4, sorry. And that's it. Now we have all of our current equations, and we finished step 2. All of our current equations, 3 amps, 2 amps, for each of the currents. So we finished that. Now we can write the KCLs for each node. Okay, so we've done all of our current equations now. So let's do the KCLs for each node. So KCL for node 1 and KCL for node 2. So let's start here. So KCLs, I'm going to say node 1 and node 2. Okay. So in terms of the KCLs, if you just think about, we're doing which what currents are going into this node here, and what currents are going into this node here. That's how we're writing it, right? So let's start with node 1. We've got I1. We've drawn the arrow as it going into node 1, right? So we can say node 1 is I1. Another way I like to do this is sometimes I put plus. So plus I1. Then we've got I4 going into it. So we can say plus I4. And then we've got 2 going out of it. We've got I5 leaving the node. And we've got I2 leaving the node. So we can say minus I2. And then minus I5. Okay, so let's do node 2. So node 2, we've got I5 going into it. And we've got I2 and I3 leaving it. So 5 in. So you put plus I5 minus, sorry, plus isn't it? Plus I2 and then minus I3. Right, okay. And then so we know that obviously all of this is equal to 0, right? Because these are the KCLs. So now we can replace, I believe we've done step, so we're finished with step 3 now. So now we can actually substitute in these I values. So we substitute in these now, these I values into the KCLs, and then we're going to do the simultaneous equations for them. So let me, just so I can have a better look at it. So node 1 is equal to I1, which we've said is minus V1 divided by 2. So we put minus V1 divided by 2. And then we've got plus I4, which we know is 3 amps. So plus 3. And then we've got minus I2. So minus I2, and we know that that is V1 minus V2 divided by 5. So V1 minus V2, all of that divided by 5. And then we've got minus I5, which you know is 2. Right? And then we've got node 2. So obviously we can simplify that a bit, but that's what we're going to do before we do our... Okay, so node 2, we've got I5 going into it, which is 2 amps. So we can say plus 2. And then we've got plus I2, which is V1 minus V2. So plus V1 minus V2 divided by 5. And then we've got minus I3. So minus, and I3 is V2 divided by 5. Cool, okay. So these are our 2 nodes with I substituted into it. And then we can just kind of simplify this a little bit more. So we can just rewrite this node 1 as minus V1 divided by 2. And then, so you got plus 3 minus 2. So it's just plus 1, isn't it? So plus 1 and then minus V1 minus V2 divided by 5. That's not great. When you write like that, you're probably going to make a mistake. Let me move that over a bit. Just make it a bit more clearer. V1 minus V2. Okay, so that's our node 1 simplified. And in node 2, we don't really need to do anything with it. So that's fine again. Okay, so we'll just write it out. We write it again in the same format. So V1 minus V2 divided by 5. I'll just write out the same. I don't want to confuse you. Okay, so plus 2, or we can just say 2. 2 plus V1 minus V2 divided by 5 minus V2 divided by 4. And there we go. So now if you know simultaneous equations, where we already know that both of these 2 equations here, both are equal to 0, right? So this equals 0 and this equals 0, right? Because Kirchhoff's current law. Okay. So in terms of getting them to be the same value, we need to do some multiplication. Alright, so we've got our two simultaneous equations, so let's now copy these. And then what we're going to do is we're going to need to get rid of the bottom denominators, basically removing the fractions. So then we can have like two actual kind of easy simultaneous equations to work with. You'll see what I mean in a minute. Okay, so we've got n1 and n2. Okay, so we've got minus v1 over 2 plus 1. So, you know, plus 1 is obviously plus 1 over 1, basically, right? So now if you look at it, like this, minus v1 plus 1 minus v1 minus v2, that's in brackets, right? All of that divided by 5, all of that divided by 1, and all of that divided by 2. Because obviously any number is just over 1, right? So now we can remove this fraction by timesing this by 5, this by 10, and this by 2. If we do that, we get minus 5 v1 plus 10 minus 5 v1, and then it's actually minus v2. So 2 times minus v2, which would be plus 2v2. That bit here is a bit tricky. You want to make sure when you're dealing with this sign, you multiply correctly. Okay, so then simplify. So you've got 10 minus 10 v1 plus 2 v2. Alright, so I was looking at this, I'm thinking to myself, what have I done wrong? But obviously here, if you have a look, not minus 5 v1, it should be minus 2 v1, because I'm timesing by 2, right? So 2 v1 there, and then that would make this bit here minus 7 v1. There we go. That's a lot better. Okay, so we've got, let's put it in terms of v1 v2. So we've got minus 7 v1, then we've got plus 2 v2 plus 10, and that is node 1. There we go. So that's our final simultaneous equation, which, as you can see, is much better than having this with the fractions, right? Okay, let's do the same for node 2. So we probably want to times, we want to get these to be the same. The common denominator, so this is over 1, right? Common denominator here would be 20. If we can get it all to 20, so this would be times 20, this would be times 4, and this would be times 5. Right, so 2 times 20 is 40, obviously. Then 4, so plus 4 v1 minus 4 v2, and then minus 5 v2. That leaves you with 4 v1. I thought I said 42. I was like, what? That's 4 v2. So 4 v1 minus 9 v2 plus 40, and this is node 2. Let's just duplicate that to be down here. Cool. Okay, all right, so now we need to do the simultaneous equations. So we've got both of these two equations, and we know that they both equal 0, right? Okay, so we need to get one of these to be the same. So I'm going to go with v2 here, right? And I'm going to get, so make this 18. So I want to get this to 18 v2 and get this one to 18 v2. And then I'll just add them together, right? So if you're not sure about that one, this has to do with simultaneous equation. So go and watch a video on simultaneous equation and come back to this one. Okay, so how are we going to do that? We're going to multiply this whole equation by 9, right? And then we're going to multiply this whole equation by 2. So n2 times 2 and n1 times 9. Okay, so minus 7 times 9 is minus 63 v1 plus 2 v2 times 9 is 18 v2, and then plus 10 times 9 is 90, and this is all equal to 0. And then 4 v1 times 2 is 8 v1 minus 18 v2, and then plus 80 is equal to 0. So now we can call this one, we can call this node A, and we can call this one node B. Right, these again. Okay, and then so now we need to basically add these together. So NA plus NB, add them together. So 8, so minus 63 V1 plus 8 is minus 55 V1, and then plus 18 V2 minus 18 V2 is equal to 0, right? So plus 0, and then plus 90 plus 8, and so 90 plus 80. So 90 plus 80 is 170, right? And that's equal to 0. So now we can say that 170 is equal to, so we add 55 onto both sides, is equal to 55 V1. And then we can do 170 divided by 55 is equal to V1. And so then we can say that V1 is equal to, what's 170 divided by 55? Any of you brain wizards can do this in your head? 170 divided by 55 is, so V1 is equal to 3.0901. So 3.09. Oh no, 3.09. We leave it as 3.09. Okay. And then so now we know what V1 is. Now we can just substitute. So I think I forgot to. So we're still doing our simultaneous equation here, right? So we've got V1 now. Now we can just substitute in V1 into either N1 or N2. So let's put it into we'll put it into N1. So V1 into N1 is, so you've got minus 7 times 3.09, right? Because it's V1, and then plus 2V2, plus 2V2 plus 10 is equal to 0. And so then we can say that, okay, so let's do minus 7 times 3.09. So answer times minus 7, and that gives us minus 21.64. So plus 2V2 plus 10 is equal to 0. Now we just need to simplify this. 2V2, and then so minus 11.64, because we're basically doing minus 21.64 plus 10 is equal to minus 11.64, which is equal to 0. And then we've got 2V2 is equal to 11.64, because we're just adding it 11.64 onto both sides, and then divide by 2. That gives us what's that, 5, choose a calculator. 11.64 divided by 2, 5.82. And so now we've got V2. So what we can say now is that we now know the voltages at these 2 points. Different color. We know what the voltage is here, and we now know what the voltage is here. So now that we know what the voltages are, we've finished our simultaneous equations part, and we're on to our last step. So our last step now is to calculate the currents using the nodes. So since we know the nodal voltages, now all we have to do is take these currents that we worked out earlier, right, and literally just substitute them in. So let's do that. By substitute them in, I mean substitute in the voltage values, right? So let's get these two voltages. Okay, make it a bit smaller. All right, so we've got the voltages for V1 and V2, and we now can literally just put V1 into here, right? So that means that we're going to have minus 3.09 divided by 2 is going to be the current value of I1. So let's do that. Minus 3.09 divided by 2 is minus 1.545 amps. Oops. 1.545. or 1.55 we could say. 1.55 amps. And then we can do V1 minus V2 divided by 5. Okay, so V1 minus V2. So what we're saying there is 3.09 minus 5.82 divided by 5. And so also what we can say here is, you see how it's minus 1.55? That's how we know that the current direction that we picked is wrong. The current's actually going 1.55 amps the opposite way. So we'll, if I remember, I'll add that bit onto the end. Okay, so we're doing I2 now. So let's do this now. 3.09 minus 5.82 is equal to minus 2.73. Divide that by 5. And we get the current again in the opposite direction of 0.546 or 0.55 amps. And then lastly, so this is I1, this is I2, and now we're on to I3, which is V2 divided by 4. So we've got 5.82 divided by 4 is equal to divided by 4. And so we got that current direction correct, 1.455 or 1.46 amps. And so now we know that, and we already know that I4 is 3 amps and I5 is 2 amps. And so now we have the current values of all of the different parts of the circuit. So we can, let's bring back our circuit. It's a bit of a mess. Okay, go through this. Maybe I can clean it up a bit. Let me try cleaning this up a little bit. So you can see here we labeled in the beginning in pink all of the current directions. So we've got I1's current direction going this way, and we know that I1 is minus 1.55 amps. So what we now can say is that I1 is actually 1.55 amps going this way, right? Going this way. And we can say that I2 is minus 0.55 amps. So where's I2? I2 is this way. So we labeled it going this way, but what we can say is that I2 is actually going that way at 0.55 amps. And then I3, we labeled I3 as going down this way, and we got that correct as 1.4, was it 46? So it's like 48, all right, 1.46 amps, 46. Yeah, so we got that correct. So that's it. That's nodal analysis. So we're finding the node voltages at these nodes, and then we're putting them into our current equations, and then we're working out the currents through each of the different branches and resistors. And that's it. So sorry that was a bit long-winded. It just is what it is. If I wasn't doing it whilst explaining it, it'd be a lot quicker. So it's not too bad. You know, if you're looking at that for the first time, you might think, what the hell is that? But it's not too bad. Just, you know, practice makes perfect, as they say. So number 1, label everything. Number 2, write the current equations. I is equal to V divided by R. KCLs for each node. Substitute in these I equations here into the KCLs. Do the simultaneous equations for the 2 nodes that you worked out, these 2 here, and then calculate the currents using, once you've got the node values V1 and V2, then calculate the currents. And that's it. Alright guys, thanks for watching, and in the next video we'll jump onto mesh analysis.